So I showed this to you last time, but I grayed out a piece of it because we hadn't done all of it. Now we've done all of it, and this is really everything that you've done on one single slide. And it actually truly is all of stats from now until we get to 308D, right? So we start by noticing something in the population that we care about, and we want to figure it out. So we want to estimate something about the population. We take a sample from that population and we investigate it. We describe it. We describe it with numbers, so things means and variances or mean differences. And then we also describe it with visualizations, right? Histograms, graphs, etc. But we have to take those descriptives with a grain of salt. And that grain of salt is how good is our sample, right? And that measure of how good our sample is what we call standard error. So we then take our descriptive statistic and our standard error, and we put that together into our test statistic, right? Those are the two components of our test statistic. And we then ask ourselves, how is it to get that test statistic if there's nothing going on out in the real world? And using that information, along with the other things we have in our, let's call it our inference toolbox, right? We then make an inference back up to the population about what's really going on. And that is stats. This is literally all we do for the whole rest of the year, okay, in one slide. Now, why am I starting us here and not on independent or dependent t-tests? Because we're still playing cookbook mode, right? So I've had a few office hours in the last week, and people are like, how do I recognize what test I should use? So this was a question in the Qualtrics, right? Can you do a comparison of all the different types of tests and when to use one or the other, right? And my answer to that question is you shouldn't be starting with tests. We should be starting with what are we trying to figure out about the population? What's a research question and what's our study, right? Because the reality is we could answer, if we just go with tests, right? There are lots of different setups that we could answer with lots of different tests. It's dictated by research question and study design, not by test. So we got to start there. So we're going to start there. So we have looked at a few different parameters out in the population. And I wanted these to go one by one. They didn't. So we're going to start here, right? So the first thing that we've looked at is we've wanted to know whether our population of interest is different from some known value. So we've had a value of the US average is 5. We want to know whether first graders read faster than this average, right? So our research question might be something, the average well-being of undergrad students is 6.4. Does the well-being of community college students differ significantly from this? We're estimating a single population mean, right? Which is the average well-being amongst all community college students. This is what we did pre-midterm, right? What we've done post-midterm are these two. The first one is, are two independent groups significantly different from one another? So is there a significant difference in well-being between students who meet with a mental health counselor and those who do not? What we're estimating is the difference between two population means. We've got two parameters being estimated. The mean of population A, bless you, right? And the mean of population B. The other parameter we've estimated is whether there was a significant change in well-being from before and after students met with a mental health professional. And here, the really important thing to distinguish is that we're only estimating one parameter, right? Which is average population change, mean difference, okay? So two population means or one mean difference. We've also investigated two different types of parameters that involve categorical variables. Do our observed frequencies differ from some frequencies that we'd expect based on some theoretical distribution? Or do our observed frequencies differ from the frequencies we'd expect if there were no relationship in the population? That's all stuff that we wonder about in the population before we've ever designed a study. Now we can go from population to sample. We're not going to worry about one sample for the sake of time, but let's talk about the things we've done since the midterm. So if we're interested in estimating the difference between two population means, we're talking about a between subject design, right? The difference is between subject. And our sample is going to have two groups and two different sample means, okay? Notice we aren't even at the test yet, right? If we're interested in mean difference in the population, right? So if I give people this intervention, how will it change them? Then we're talking about a within subject design. And we have one group with one mean difference. Now, sometimes you're given those difference scores, and sometimes you're not. Sometimes you're given people's first measurement and their second measurement, and you need to calculate that difference score. But the important thing to know is that we've got one group, right, with two measurements from which you can calculate a difference score. Notice it's the design that's driving, right, what the data look like. One is between subject, one is within subject, right? And then we've got our observed versus expected frequencies, our categorical version. And here, our sample data are the same. It's always observed frequencies. So we have observed frequencies in our sample. So that's our descriptive data. That's what we have in our data, right? We've got means, we've got mean differences, we've got observed frequencies. And now what we want to do is do something with that descriptive data. We want to test it, right? Right now it's just descriptive. We want to test, we want to use that descriptive data to test our research question. But before we actually do that, before we put that mean, if we have these two means right here, right? These two sample means, before we put those two sample means into a hypothesis test, we have to evaluate the quality of the sample, right? And in order to do that, we need standard error. Ask ourselves the question, how good is our sample? Or more specifically, how off is our sample? This is pre-midterm heavy. We went real hard on standard error pre-midterm. So I'm not going to spend a ton of time talking about it. If you want help on standard error, this would be a good thing to nail in office hours right after class today. But I did throw one slide up, right? Which is it's the degree of offness of our sample. So remember that the way that standard error works is that every individual sample, this was a great question from Sean yesterday. Sean asked me an awesome question, which is there one sampling distribution or one sampling distribution for every sample? Every single individual sample that you pull in a research study has its own theoretical sampling distribution. So, for example, if Madlena and Hannah were to run a study on 100 people, there is a theoretical sampling distribution of n equals 100 that exists in the ether as if they resampled infinite number of times with n equals 100. And that sampling distribution is based on their sample size and the spread of their sample, right? Because those are the two things that indicate how off your sample is from the true population. So we only take one sample, and it's either this big or this big, right? If it's this big, we didn't capture very much. If it's this big, we captured a lot more. If it's really spread out and kind of wacky, right, we probably didn't do a good job capturing a good mean of the population. If it's really tight and narrow, it's more representative. Those are the things that indicate how off our sample is, right? So there is a theoretical sampling distribution that belongs to every individual real empirical sample that we pull as researchers. Okay? So we've got our descriptive stats, our means or our observed frequencies. We've got our standard error. Here's a question, does standard error apply to chi-square? Think this one, it's not a Rolodex. Look at the two things that make up standard error. Now tell me if this is a logic problem, not a Rolodex. If standard error is made up of the standard deviation of your sample and sample size, can chi-square have a standard error? No, right? It doesn't have standard deviation. So we take those two things together, and what do those Our test statistic, exactly. They are literally the two puzzle pieces, the two pieces of our test statistic, right? Good. So let's deep dive into test statistics a little bit. Now, I'm going to hold on chi-square until we get to chi-square, because chi-square is a little bit, one of these things is not the other. It functions differently because it's got its only categorical variables. I want us to deep dive on t and z together because they function similarly. So here are those parameters we've investigated. Now we can ask ourselves what test we might need to run, right? So for a question that is asking about differences between two means between subjects, we will use an independent t-test. If our research question is asking about change and we have average change, we're going to be running a dependent t-test. I told you already that there's no chi-square goodness of fit. If we want to know, this one's pretty easy for test ID. If we want to know whether two purely categorical variables are related, your only option when both your variables are categorical ever is chi-square, right? Ever. Now, let's dive into test statistics. Scale of 1 to 5, how nervous does this slide make you? Yes. Right. Yes. That's what I anticipated, and I think that that's actually part of the issue. For some of you are, I love equations and math, so this slide makes me happy. I'm not talking to you, right? I'm talking to the people who are, when you look at this slide, right? The people who are, I mix up numbers all the time, and so this gives me anxiety. The reason that I'm doing this is because I think one of the things that's happening is, I also, by the way, when I look at this slide, get a little bit of anxiety. Pretty things. This slide's not pretty, it's just a bunch of formulas. Sorry, if you have formulas, maybe it's pretty. But the challenge is that at first glance, it's a lot of numbers and formulas and symbols. But if you can slow yourself down, it's actually really patterned, right? And what I need us to be able to do is to get past the kind of jumble of it and see the conceptual pattern in it. Because otherwise, it's gonna throw you when you need to use it. So I'm going to start here in the scary, and I'm going to go to another slide where I tried to make it not scary. And then I'm going to go back to this and we're going to see how scary it is after that. Deal? And we're going to not talk about I put a line because we're not going to talk about chi-square right now. Just going to talk about z and t. First of all, we know this already. Z and t is a ratio of two things. What are those things? Effect and error, right? As one student loves to call it, treasure and trash. Right? So effect and error. What are the three effects? We've only covered 3 types of effects in Z and T tests. We've covered the difference between a sample mean and a number. So the average well-being in the US is 6. Your sample has a well-being of 9. Are those different? That's an effect of 3. Don't overthink it, right? That's the effect, a distance of 3. You good so far? Yeah, that's the effect. The second effect we've covered is the difference between two sample means. So my first class has an average of 50. The second class has an average of 55. What is the effect? 5. It's a difference of 5. And then the other effect that we've investigated is the average change, right? Students reported an anxiety of 10 before the mindfulness intervention and 8 after the mindfulness intervention. What's the effect? 2. Any questions about that? I want all, please ask them. I don't want to keep going if that part's not clear for anyone. Any questions about how I measured those effects? Literally, it was just means. No? Good? And give me some verbal confirmation that it's good. Some sort of confirmation. Thank you, Asia. So that's what we mean by the numerator of a t. That's it, right? So whatever the weird symbols are at the top of this formula, that's all. So now we've covered the numerator, not as scary. So now let's talk about the denominator. It's a little scary. Error we've covered. Guess what? We've actually only covered one type in the denominator. What is it? It's just standard error. So the denominator of our test statistic is always some version of standard error. Okay, standard error tells us how off our sample is. And we just talked about it. What are the two things that go into standard error? Standard deviation and sample size. So guess what? The formula is the same for all of them. It's just spread and size. That's it, right? The denominator for all three of these is spread over size. So it's, thank you. So spread over size, right? Now, the question is spread measured the same in all three of these? No. Is size measured the same in all three of these? Kind of, right? Is n always size? Yeah, right? There's more consistency there. So let's figure out how spread is measured in each of these. How is spread measured in a z-test? What's unique about a z-test? We know something in a z-test that we don't know anywhere else.
Population standard deviation?
Yes, we know what? We know the population standard deviation, right? Good. How about a one sample t-test? We don't know it, but we know the sample, right? So look, it's just spread. So we'll do spread in blue. Here's spread, and we'll do size in yellow. Now, how about, I'm gonna skip to dependent. What's spread in a dependent test? Spread of the difference scores, right? So that's really important. The reason I drew this on top is a reminder that we're not working with two distributions in a different score. We're working with one, right? Here's the mean difference, and this is the spread, right? So we've got spread. So that's just going to be same standard deviation of the difference scores over n. Good so far? Now the scary one, the more scary one. It's not the more scary, it's the one that you guys have been, it's you have this, if I don't know right away, I'm not going to dive in and try to figure it out. So the number of questions I got about pooled variance that I'm actually very confident that you could figure out if you just pushed a little. I'm not actually going to tell you the answer. You're going to tell me, right? So now, standard error is spread over sample size. What's the spread here? Or what's the problem in figuring out what spread is? There's two. Shoot, which one do I use? Both. What might I want to do? What might I want to do with them? Pool them, right? Yeah, I can put them together, right? Even if you just said, I have to put them together somehow, right? Yeah, we have to somehow use both spreads, right? The spread of group 1 and the spread of group 2, right? And what about sample size? We've got 2. We have to somehow put together the sample size of group 1 and the sample size of group 2. So it's the same formula, it's spread over sample size, but we have 2 spreads and 2 sample sizes. So before we do anything, we have to pool those spreads. So the formula, right? And what I did was I separated it out into the one that looks more like all the others, right? So really, it's just pooled spread over each of the 2 sample sizes. Now, that's no different than what is on this slide. This less scary now? A little bit? A little bit? No? Less scary? Same scary? Yeah.
For the notations, do we have to like be exactly consistent?
What do you mean by that?
If we're writing over this, like writing out, I mean that what we write are like calculations.
Okay, so 2 things. One, I already told you the 3 calculations that are going to be on the test, right? None of which involved pooled variance, right? So there won't be. And 2, I do never care how you notate your things. Yeah, ever. No, you can note. I notate it this way to help you keep track of things, but you can notate things however you want. Yeah, yeah. But no, there is no pooled variance on the exam. Yeah. Again, because here's what's happening to your brains. Here's what I want your brain to do. I want your brain to go, oh, I need to recognize how off my sample mean difference is from the population. In order to do that, I need to consider the spread, right, of both of my samples. That involves pooling the spread of both of my samples, right? So I have to pool the variance of each of my samples. That's what I want your brain to do. Instead, what your brain is doing is, What's the formula for pooled variance? Oh my gosh, do I multiply by degrees of freedom? And then you're trying to do the math and making a mistake and your brain is being directed in the wrong direction. So I don't want you calculating pooled variance on the exam because it's making you think about the wrong thing. Does that make sense? Cool. So why don't you use pooled variance in a dependent T? Did that clarify that? Because there's only one distribution that we're working with there, right? We don't actually, even though there's pre-scores and post-scores, right? We are first creating different scores and using a single distribution for that. Can you find, this was a great question. If you have, you know how you get the individual estimated standard errors in the output? You can't use those to get pooled variance. You can't use those. You have to, the reason in number 5 that you had the data was because you actually had to calculate pooled variance in number 5 in the review questions. You can't use the individual estimated standard errors to get pooled variance. Cool. Questions at all about the test stat? Yeah.
It's a dependent t-test.
Yep.
Could you subtract
Yes.
standard error?
No. No. Yeah, if you have standard, if the question was is if it's a dependent t-test, could you subtract the standard errors? Wait, the individual standard errors to get what?
I guess you're not.
Yeah, you're only looking for the standard error of the different scores.
So we'll give it to you.
Yes, it'll give it to you. Yeah, yeah. Questions at all about that? Was that helpful and clarifying? Yes, questions? No? This is on here for you. I'm gonna just leave it alone. The degrees of freedom we're working with right now are relatively simple. NHST, there, so what I put on the slide, I put some of the slides from the midterm review in here, just the 4 possible outcome slides. That content is not on the exam, alpha, beta, type 1, type 2 error stuff. I shouldn't be hearing excitement about that though, because that is going to follow you for the rest of the entire year. So if you don't feel solid about that, it's worth reviewing because we're going to be hypothesis testing for the rest of the year. But for the sake of time, I'd rather spend time on the power, effect size, that stuff. But I do want to answer this one question that came up, which is, what is the relationship between alpha and beta? So alpha and beta are in different curves, remember? So if you look here, alpha is in our null curve. That's our rejection region, right? It is also our probability. This is a question on the midterm. It's our probability of making a type 1 error, right? So we're going to reject anything that is here. Here we go. We're going to reject anything that's in that red zone, right? And it could be, in fact, in the null curve, which would be a type 1 error. If we shrink our alpha down, right? Or let's say even actually if we increase our alpha, that's going to make it more to find an effect, right? However, let's look at this. If we moved our alpha to here, right? That would make it more to find an effect, but it would also what? It would increase your type 2 error, right? So they're inversely related in that way, not numerically, just conceptually. They're not numerically related in that way. It's not the values add up to something, but they are trade-off errors. You can think about it that way, right? So if you, yeah. Sorry, if you go this way, you increase 1 error. If you go this way, sorry. Yes, thank you. Yeah, thank you. I just misspoke. Yeah, thank you, Ray. So if you increase your alpha, right? You make it easier to find an effect, but you increase the type 1 error, right? Because you make your rejection region larger. And if you decrease your alpha, you avoid type 1 errors, but you make type 2 errors more likely. So that's why we didn't have this question on the exam, but I think we had it on the DA, which is worse, right? And that's really up to the researcher and what the research question is. So you as a researcher have to determine, in this case, which is worse, making a type 1 error or making a type 2 error. And that sometimes impacts where you set your alpha, your rejection region, depending on the context of the research that you're doing. Let's go. It's 9:50 is the good break time. Let's take a break until 10, and then we will do an HST under the hood. From here on out, it gets a little bit more you do, as then you're going to be doing some practice stuff. So make sure you have stuff to write with after we can. All right, NHST under the hood, the stuff that really matters. This is pretty heavy on the exam because it's heavy for the rest of stats. And it's a lot of the answer to why things happen in your design. So we keep coming back to it quite a bit. First of all, p-values. My goal is that 100% of us nail interpretation of the p-value, right? Realistically, we will. We're gonna do it. So again, probability of obtaining this result or something more extreme, assuming the null hypothesis is true. How is it that you get this result if there's really nothing going on? This is a great thing to have on your cheat sheet in terms of your sentence frame and remembering what parts you need to be able to put back into context. So there's a 0.042, I guess I should probably highlight this also, right? There's a 0.042 probability of obtaining this result or something more extreme, assuming the null hypothesis is true. So our job is to take this result and the null hypothesis part and put that back into context. When I say into context, I'm going to define into context more clearly for you. Into context research understands what you're talking about. So what I mean by that is if you just say the probability of getting a mean difference of 4.7 or something more extreme, that's not really in context, right? Because what's my follow-up question going to be? 4.7 what, right? So if we're running an independent t-test looking at the difference in productivity between people who exercise regularly and those who do not, what's the context? More than that. Good. The context are differences in productivity based on exercise, right? That's the whole context, right? If I just went out in the world and someone was, what are you studying? And I said exercise, that's not complete context, right? If I just said productivity, that's not complete context. It's got to have the whole context. So there's a 0.042 probability of obtaining a mean difference in productivity of 1.64 or something more extreme, assuming there truly is no difference in productivity between people who exercise regularly and those who do not. So notice I put the rest of the context in the null. That's fine. It doesn't matter where it goes. I could say a mean difference of productivity of 1.65 or something more extreme between those who exercise and those who do not. That would be fine too. It doesn't matter where it is as long as the full context is somewhere in the interpretation. Right? A research study was conducted to examine how perceptions of life satisfaction change as people age. 10 adults were given a life satisfaction test once between 20 and 30 years old, and again 15 years later. Scores on the measure range from 0 to 60, with high scores indicative of high life satisfaction. Low scores indicative of low life satisfaction. The output is below. Before we interpret the p-value, right? 1, what type of design is this? What type of design? Within subject. How do you know? Same group, measured twice, right? So 10 adults were given a life satisfaction test once between 20 and 30, and again 15 years later. So given it's a within subject design, now what type of analysis are we going to use to analyze it? Dependent t-test. Good. What is our predictor variable? This is good. Dependent is harder for this. Let's do this. What's our predictor? What's our predictor construct?
Age.
Good. What's our outcome? Life satisfaction. What's our operationalization of age? Careful here.
Young and it's not actually the ages.
Good, right? We only have 2, we're operationalizing age not as a continuous number here, right? We're operationalizing age as measure 1 and measure 2. So we can opt to call it something, right? Young, let's say, is 20 to 30, or we could even, if we don't want to give it a name, we don't have to, right? So the operationalization is 20 to 30, or what's the other one? 15 years later, right? So I guess we'd say, yeah, 35, right, to 45. And what's our operationalization of life satisfaction? Scale from 0 to 60. We don't know the anchors, right? Good. What's our variable type? What's our variable type of age? Categorical. How many levels? 2 levels. What's our variable type of life satisfaction? Continuous. Good. Now, interpret the p-value. Go. Everybody do it. Write it down or talk to each other. Don't just look at it and go, yeah, I can do the p-value. Do it. Do it. You don't get to look at the exam and go, yeah, I can do it. I wish. The list of questions.
No, I think, that's based, whatever number. Regardless, whatever that numbers. But. Yeah. There's pattern based on whatever.
Yeah, we're talking about. So you have to probably, I don't know, different. Yeah, we're talking about what is different. I think they. Because in the summary, you don't actually. Yeah, if it's for the independent teachers, you would care more about the 2 different levels. We need more time. By just, all you be, in order to do that, yeah, you're right. Changing alpha changes theta to do that. Because what you would be doing is just moving the alternative, not gonna say it. Yes, thank you. Yes. This is.
Yes.
So while we're interpreting the p-value, should we take the mean difference or?
The individuals? Good question. That was exactly what I was about to start talking about. So when interpreting the p-value, should we be focusing on the mean difference or should we be focusing on the individual means? Well, in this example, there's a clear answer. In an independent t-test, there's less of a clear answer. In this one, there's a very clear answer. Why? What are we actually testing in a dependent t-test? Different scores, right? We get these, but that's not the hypothesis, right? In a dependent t-test, the null hypothesis is no difference, right? And the alternative hypothesis is that this is significantly different than 0, right? That's literally what we're testing. So in this type of test, we want to focus only on change. In fact, Jack asked a good question, which is when putting it back in context, how much should I even focus on these 2 levels, right? Because really think about storytelling, right? Interpreting P is about storytelling. The story here isn't, there's a difference in when we measured them the first time and when we measured them the second time. The story is that as adults get older, right? That's the story. So when we're talking about a dependent t-test, we care about change, right? Or growth. And so in this particular example, whereas with an independent test, we really do care about the difference between the 2 different groups. Here, what we're really talking about is the process of change, right? And so in the interpretation, in the storytelling, I probably wouldn't opt to even talk about time 1 and time 2, or when they were young and when they were old. I would probably use language as they get older, right? Or as they grow. Because that's really the story of what's happening here, right? The story of what's happening is that as adults get older, what happens? They get happier, right? God, I hope so. Yeah.
The main difference.
Yeah. Hold on one second. Yeah, Emily?
You might not know the direction.
Totally. You need to use the means to understand the story internally, but you don't need to use the means to articulate the story necessarily. Yeah, but yes, if I just look at the -16, I don't know right away without having set it up. I need right away to know, yeah, I don't not need these. That's why I included them, right? I need to know time 2 is 44, time 1 is 28. You're happier, and I know that's significant. You're happier when you're older, right? But now I'm going to talk about it as you get happier as you get older. Because it's not two different groups. It's not the older people were happier than the younger people, right? Because it's one group of people. Somebody give it a shot. How to interpret the p-value?
Assuming perception of life satisfaction doesn't change as people get older, there's a 0.007 probability of getting a difference of 16.4 or something more extreme.
Want to give me another one? Right.
Assuming the lowest strength in life satisfaction based on age, the probability of finding a difference of 6.4 between more extreme is equal.
How can we contextualize the difference a little more? Yeah.
Talk about the decrease, so the probability of finding a average life satisfaction classification score increase of 16.4 or extreme between young and old. That
Awesome.
level of assuming.
Awesome. Yeah. The nulls are beautifully contextualized, right? Assuming, and I love that those were different. So assuming that there's no relationship between age and life satisfaction, that's a beautiful way of saying it. Or assuming that life satisfaction doesn't change as we get older. Those are both beautiful ways of saying the null, right? And then the probability of getting a difference of 16.4, but we can contextualize that more, right? We can say the probability of life satisfaction going up by 16.4, right? As our participants got older, right? So don't forget, you're interpreting the P as in you're actually telling people what happened in your study. That's the result, not just the number. Think about the result not as the number, but the result. So here's what I wrote. Assuming perceptions of life satisfaction scores don't change over the course of one's lifespan, the probability of seeing this increase in perceived lifespan of 16.4 or something more extreme as people age is only 0.00. Okay? All three of those are fine. Questions at all about, so that's a good note to yourself. Result means actual study result with effect, not just the effect. Storytelling. Interpreting is storytelling. Victor.
Your answer said perceived lifespan,
No, it's over the course of one's lifespan.
no, after that, seeing the increase in perceived lifespan.
Sorry, that should say life satisfaction. Yeah, thank you. Yeah. Told you. Yeah.
Confused because although the outcome variable 0 to 16.
Yeah. The outcome variable is not 0 to 60. Oh, the outcome variable. Yeah, it's, yeah.
But we are classifying them as low score, which can make them
No, we're not classifying it as that. We're just telling you that higher scores, 0 to 60, if you tell someone that a scale goes from 0 to 60, you don't automatically know that 60 is good and 0 is bad. That's all this means. With higher scores, right? 60 is high satisfaction and 0 is low satisfaction.
that is just explaining.
It's just explaining the anchors of the scale. Yeah. Yep, cool. Yeah.
Why interpreting the P value? Why do we take mean difference like 16.40 instead of T?
Because T doesn't mean anything, right? In terms of what you found in your study, right? So what's your research question?
I mean,
What's the research question?
judging your age affects lifestyle.
Right, and even more specifically, do we get happier as we get older? If I tell you that I found a T if I tell your friend that doesn't take stats that I found a T of 3.4, right? She's gonna be like, I have no idea what you mean, right? If you're, oh, I saw an increase of 16.4 in life satisfaction, you've just told her exactly what your answer to your research question. So it gives you the actual result of in alignment to your research question, whereas a T is, the purpose of the T is purely for us to be able to infer back to the population in an hypothesis test, but it's not actually the effect we found, right? T is this, remember that the T stat is effect over error, right? 16.4, that's our effect, right? So the result we got is our effect. T is what tells us whether that effect is significant or not. Make sense? Any other questions about this one?
Just a quick question.
Yeah.
So in this instance, you said interpret the p-value, and when I was writing notes down, I also went over to effect size and added that too. But if you ask a question on the test to say just interpret the p-value, don't worry about it unless you specifically say make sure to include effect size or
Yeah. If I want you to interpret the effect size, I bet you can guess what I'll say. Interpret the effect size. There are those. We'll get there. Yes, there will be those. And then, but that is a good, just while we're here, right? But while we're here, how would we interpret that effect size? What's the first thing you would do to that effect size? Yeah, make it positive, right? Ignore that negative. Why?
It's kind of what's.
Yeah, what unit, this is really important, what units is the effect size always in? Standard deviation, right? Between 2 points, it's a distance, right? Cohen's d is a distance. Can distance be negative? What does a negative distance imply? Directionality, that's a beautiful way of saying it, right? It just shows which one is higher or lower than the other, right? Cohen's d is not designed to tell you about directionality. You can do that as a researcher yourself. You're gonna tell me which one's higher or lower. This just tells me magnitude. Think about it, absolute value, right? It's just distance. So how many standard deviations away were these two measurement points? 1, right? So people's life satisfaction when they were older was about a standard deviation higher than when they were good. Now let's talk about definitions. You've seen this slide before, but it has an addition to it to clarify some misunderstandings that have come up. And there's an additional slide coming up that's new. So statistical significance is a conclusion that we make as researchers that there is an effect. Power is the probability of finding an effect that's actually there. Here's the new one. We're confusing this concept of effect and effect size. So I want to clarify. There's not really a term for it, so I'm sort of making it up. I'm going to call effect whether or not there's a relationship between the stuff you're studying. That's not the same as the calculated effect size that you get in your study, right? So, for example, if social support impacts life satisfaction, it either does or it doesn't. You can't change that, right? But there's also going to be an actual, let's say you're running a t-test, there's going to be an actual Cohen's d in your study that you calculate too, right? That's your calculated effect size. Your goal is if the effect exists out there, that you get it, right? That you find it. If it's not out there, you can't find it, right? So that is the precursor, right? The power is that idea that that effect is out there and you find it. Sample size, we know, that's easy. So now let's contextualize those a little bit. So let's say group A meditates every day, group B does not. Is there a difference in happiness between group A and group B? Statistical significance is the conclusion that group A is not statically different, statistically different. Maybe they're statically different too, but statistically different from group B in happiness, right? Effect is whether or not meditation has any effect on happiness, right? It either does or it doesn't out there in the world, right? If it has no effect on happiness, then no study we can run will make it have an effect on happiness. If it does affect happiness, we can still have a study that doesn't show it does, right? We can fail to find a real effect. Ideally, our power is such that we do find the effect if it's out there in the world. We will also calculate an actual effect size, which is the magnitude of difference in happiness between group A and group B. This one we can impact, right? So this is the part that's sometimes getting confusing. I can't change whether meditation impacts happiness. It either does or it doesn't. I can't even change how much it does, right? What I can change is, given the effect out there in the real world, I can make that effect show up more in my study, right? By increasing dose. So let's say for a second that I have a crystal ball and I know that meditation does in fact have a huge impact on happiness. Well, if I make people in my study meditate for 3 minutes, my calculated effect size is gonna be trash, right? If I make them meditate for 30 minutes every day for a month, I'm gonna see a bigger calculated effect size. Did I change the impact of meditation on happiness out in the real world? No, right? I just changed my study design to illuminate that effect, right? You can think about it as the real world effect exists, but you can illuminate it if it exists, right? Sample size, we know, and then power is the probability of finding a statistically significant difference between A and B when in fact they are different. Are you out there? Yeah, cool. So when do these things happen? Statistical significance happens post-analysis, right? We decided it's a function of effect size, sample size, error, alpha rate, effect, actual out there in the world effect. That's pre-analysis. It is what it is, right? This is the only one here where we literally have 0 touch. That's just the world. Pre-stats, pre all of us, just how things work. Calculated effect size is post-analysis, right? So we calculate it afterwards, but it's a function of the effect we find in the study and spread in our data. Sample size is pre-analysis, we decided, and power is pre-analysis, right? It's a function of effect size, sample size, and alpha rate. We calculate that probability going into the study. Yeah,
So then really it's logical with the statistical, I mean, statistical significance is free and then the power is low.
opposite. Post for statistical significance, pre for power. No. Power is a probability of finding an effect that actually exists, right? So let's assume for a second that there is an effect of meditation on happiness. We want to be able to find it. Power is the probability that we will with our given study design. So we design a study, and given our study design, there's an actual probability from 0 to 1 that we will find an effect if it's there, right? Statistical significance is after we do our study, we are going to make a conclusion about whether there's an effect. That conclusion is statistical significance, but that conclusion is not necessarily right. We could be making an error, right? So that happens on the tail end. So now let's talk about power a little. Oh yeah.
And how is pre-analysis when it has effect size?
Next slide. This is the new slide. Also, this was my first time playing with ChatGPT images, where I was like, make me a machine with this, this, and this as inputs, and this as an output, but make it reciprocal so that you could also do this as an input. So check out what it came out with. Pretty cool. Like I said, I'm solo by myself. This is what I did with my spare time. So power is the probability of detecting a true effect. We don't calculate actual power in here because the formulas to do it by hand are super duper complicated, right? You can, but they're really complicated. So it's much easier to do it either in R or in a program, GPower, for example. But I am going to at least conceptually show you what is happening under the hood of the formula right now, because I think that helps you understand how power actually works, because there's still some confusion about what it is and what we mean by probability. So first of all, power is a probability, right? That means it goes from 0, no shot in hell, to 1, 100% certainty, right? Literally, you go into a study with a level of power you feel comfortable with. So I say, like, what is something someone studies here that you care about?
Employee engagement.
Great, employee engagement. You want to know whether principals lead to teacher engagement, right? Principal leadership has an impact on teacher engagement. Assuming it does, what probability would you that your study finds that result? We don't 100%, right? But there's trade-offs. We can't do that. Because 1, you need 1 million people. Good luck. You need every charter school in the country, right? And 2, you'd have to mess with alpha rates. You need huge effect sizes. It's really hard. But what would we be comfortable with as a probability? 0.9. So we're saying if principal leadership, say principals, we get narrower. Let's say feedback from principals. If feedback from principals really impacts teacher engagement, right? She would have a 0.9 probability of finding that effect. right? She would like to be 90% sure that her study finds an effect. So we're landing at 0.9 to her study. So then the question becomes, well, what goes into getting a power of 0.9? 3 things: estimated effect size, alpha level, and sample size. Now, alpha level, we usually don't mess with, right? We usually tell our power analysis tool, whether it be G-Power or R, I'm going to use the two-tail hypothesis test at alpha 0.05, right? We don't usually mess with it. Estimated effect size, usually there's 2 options. We can use previous literature, right? We can say, I'm going to scour the feedback literature, maybe a meta-analysis, and I'm going to look to see, probably we're doing a regression, not a t-test here. So what's the average beta size that I'm working with? Or even more common is we'll aim really low, right? So if you think about the Cohen's d brackets, you choose the lowest one, right? You can even look in the stats literature for what's a rule of thumb for estimating effect size in a power analysis. And I think it's usually around 0.10, right? Or 0.15 for a regression coefficient, so that you're always being more conservative than you need to be, right? So you say, I'm going to estimate 0.10, I'm going to go with 0.05. I don't know how many people I want. That's the whole point. But I know I want a 0.90. Well, guess what? Now I have all the pieces of the power equation. It's not a simple equation, but I have all the pieces except sample size, right? Now, what that software is going to do is tell me this is the number of people that you need in order to have a power level of 0.9. And look at the cool thing it made me. It's so cool. That's pretty cool, right? Literally from my description. ChatGPT made that for me for my description. This is what I do with my spare time.
Out the poofs.
Thanks. Except, yeah, that was mine. I said, please say poof when it works. Literally. Except for some reason, why does it say sample size? There's some weird, it does that, right? Yeah, there's some weird spelling things. Yeah. So when we say power, right, it's a probability that's influenced by these 3 things on the front end. That make a little more sense? Yeah. So if we're interpreting a power of 0.8, we're saying there is 0.8 probability of finding an effect, assuming it is actually there, out there in the real world. Yeah, kind of.
I figure there's some sort of relationship that I had asked a similar question to this last week, but I don't know how relevant it is right now. But is there a relationship between power and
Relationship, confidence intervals, effect size. The only relationship between power and confidence intervals, very abstractly, I'll answer it really abstract. So technically when we're calculating power, it's done on the front end, right? So the effect size we're using is not our actual effect size, it's an estimated effect size. But if you think about what makes up effect size, spread is in there, right? Spread is also in standard error, which is in confidence intervals. So that's the abstract relationship, but the spread is different because one is a priori and one is post calculation. Yeah, that's a doozy. I had to think about that. Yeah.
Can I ask you a quick question?
Yeah.
What do people normally shoot for in terms of power when they're working
Yeah.
on it?
0.8, 0.9. 0.9. What do you guys use? 0.8, 0.9, 0.8?
I 0.8 in my thesis, and Jason said I fear 0.8 power, so I had to.
Okay. That's why I said 0.8, 0.9. I made everyone happy, right? 0.8, 0.9, 0.8, 0.9. It also, I mean, the other thing is, I think all of us, at least I will say, it depends on the size of the effect we're working with, right? Because remember, as you change your effect size, that changes the number of people you're dealing with. So if I do 0.9 and it tells me I need 4,000 people, I'm going to be like, yeah, maybe 0.8 works this time, right? We fudge a little. Everything in stats, this is the Siegel line in survey. Everything's a trade. Yeah, same in stats, right? Everything's a trade-off. So yeah, I might get a 0.95 power, but I'm also going to shell out $20,000 to recruit 50,000 people. So let's keep going because we got more to do. Things that influence power. Just remember, this is a priori. So now you can use this piece, right? Well, how do we actually increase our rate of getting an effect? Well, look at the things that go into it and we can answer that question, right? We can what to our sample size? Increase it. We can what to our alpha level? Careful here. What do we do to our alpha level?
Increase alpha level.
Nice out. I like that. Let's look at this. Think, right? Look at this right here. What's power? Finding an effect that's there. So in order to have power, we have to actually find statistical significance, right? If that were our obtained result in green, we're retaining the null. What would we need to do to our alpha to actually capture, to reject the null? We would have to increase it, right? So increase alpha. Think, don't memorize. That would have been a good, when I asked that question, that would have been a good time to sketch, not Rolodex. I'm trying to get us out of some bad habits. So I say that lovingly, not, this is lots of years of. Next one, sample variance. So this goes actually to Catalina's question around spread, right? Effect size has two things in it, right? Effect and spread. So we can increase this component of power by either increasing the top part, by increasing dosage, so how far apart the means are, let's say, or decreasing spread. Those are the two ways to increase that third component of power. Really, if you need a reminder of what that looks like, right? If we're doing a dependent t-test, the Cohen's d is the effect, right? So if we can make the change bigger by increasing dosage, that will help. And if we can decrease the spread, that will help. This is effect size for Cohen's d for a dependent t-test. That's that third component. That's where spread, okay? Cool. Now, the sample effect size statistical significance piece, right? So remember, our goal is power. Our goal is not statistical significance. Statistical significance is required for power, meaning we can't, power involves finding an effect, but finding an effect does not mean there's actually, declaring statistical significance does not mean that there's actually an effect, right? So the relationship between effect size and sample size, or effect and sample size, right, are complementary in that way. So if we have a really tiny, tiny effect, we need a huge sample in order to find it. But the opposite is true. If we have a negligible effect and enough people, right, we can find statistical significance even though that effect is not practically meaningful in either way. There was some confusion about this on the midterm, so I wanted to clarify a little bit more about why. So here, so what does it mean then when I say, what does it mean that NHST is biased by sample size? This really belongs in the limitation section, but it relates so much to power and statistical significance and effect size that I wanted to include it here. So here's our null hypothesis. There's our rejection region of 0.05, right? The T critical, this is for a degrees of freedom 98, so 100 people. The T critical for this test is 1.98. So what that means is that any T calculated that I calculate that's bigger than 1.98, I'm going to reject the null and conclude statistical significance. Any T lower, I'm going to retain the null and say not statistically significant. Cool. So now let's look at the actual T formula. So remember that in words, T is effect over standard error. And that means it's effect on top and spread over sample size on the bottom, right? Now, what would happen, right, if my effect were really, really small, but I jack up my N really, really huge? What happens to my T? If assuming I do nothing else, but I increase my N, what happens to my T? It goes up, right? And then what happens to my actual literal T? It goes further into the rejection, right? So all things held constant, right? If you up your sample size, you are more to reject the null hypothesis. Now, look at effect size. The formula for effect size is the conceptual formula. Sample size in it? No, right? That's a really important distinction I think people are missing. There's no sample size component to effect size. It's just effect over spread. So the effect is going to stay what the effect is, But as I jack up sample size, I'm gonna become more to reject the null hypothesis without changing that really tiny effect. That's how we end up with that situation where the effect was small, but we increased n so much, right? That whole standard error got teeny, and we declared statistical significance even though that effect size was tiny, okay?
Can you go back to the previous one?
Is it quick?
Okay, no, no.
And then let's take it offline, yeah, just because we have left. That makes sense? I want us to know why, connect those pieces. Limitations and alternatives to null hypothesis significance testing. Should we trust p-values? I'm not, this is just, these two are just repeats of last time. So the bottom line is, why don't we trust p-values? Couple of reasons. One, big one, they're binary decision-making points, right? Remember that you know how to interpret ranges of p-values. So if I say it's 0.042, you know where that is on a null curve, right? If I say it's 0.051, you know where that is on a null curve. But really, it's a binary decision. Statistically significant, not statistically significant. That's it, right? It's biased by sample size. We just looked at that, right? You can jack up the sample, find statistical significance, even when we have a less practically meaningful effect size. Sampling bias, right? It's a one snapshot in time, right? This is a replica of 7 different samples. You can see sometimes it's significant, sometimes it's not. Here, by the way, here's another example of bias by sample size. This is a really cool example because the stats are identical. So look at the mean. Here's the mean of the control group and the mean of the experimental group. They're the same, right? One has 40 people, one has 4,000 people. The 40-person one, not significant, 4,001 significant. Crazy different p-values and t-values. Isn't that crazy, right? Don't forget, this also goes to your question about why mean difference and not t. These don't ever get divorced, right? Those go together. T's without p's don't exist, right? T's are just values that correspond to p, and p are probabilities that correspond to test statistics. So always think about those as a unit together. Test statistics and their corresponding probabilities. So the goal of inferential statistics is really to understand what's happening in the population as best we can, right? The reality in stats is that there's no such thing as knowing the truth about what's happening out in the world. Instead, it's figuring out all the things that we have in our toolkit to understand what's happening. We never have all the puzzle pieces, right? We have some really clearly defined pieces, p-values, confidence intervals, effect sizes, etc. But then we also have unique things that are just happening in the context of our studies that are also important pieces for making sense of what's happening in the world. So it's really, that's where that holistic storytelling part comes into play. And we can't sort of get lockstep in stats about what's happening, or we miss those really important breadcrumbs along the way of what is really happening. So what do we have in our current inferential toolkit? Well, we have significance, right? The probability of getting this result, assuming no effect in the population. We have directionality, the direction of our results. We have effect size, which is the magnitude of the effect that we found. And we have confidence intervals. How confident are we in our sample result? So these are the 4 sort of tools we have in our toolkit right now. We've talked a little bit about effect size. I'm going to do a quick review. I'm putting these 3 on the cover slide. This is in here. This is in here. I've never talked about omega, right? I just want to make sure. That's in the book. We're not using omega for anything we've done so far. We will eventually, maybe. I teach omega in factor analysis and structural equation modeling, but we're not going to use that as a measure of effect size in here right now yet. Cohen's d and eta squared. So remember magnitude of effect. When we're talking about a z-test, an independent t-test, and a dependent t-test, they all use Cohen's d, which is a measure of the 2 most important things to understand about Cohen's d is that it's a measure of distance, linear distance, right? So as in, how far away am I in a line to Tatiana, right?
So they are a measure of distance, which means it can only be used for 2 points, right? Once we get to more than 2 points, we can't use Cohen's d anymore. So it's a measure of distance and it's in standard deviation units. That allows us to use it as a measure for any type of variable. And if you notice, this is another great example. Look at all three of the formulas and tell me in English words, what's the numerator and what's the denominator? What's the numerator first? Effect. What's the denominator? Spread. Good, right? So the numerator is effect. It's the particular effect in each one of these tests. It's actually the same effect as the test statistic, right? And the bottom is just the spread without the sample size component, right? It's not standard error, it's just the standard deviation. There are examples here for you of how to interpret them. We always interpret them positively because they're linear distance and because it's a different tool than directionality. Bless you, or cough. Do it. Bless you. And then cutoffs, again, I've said this before, I don't really care that you're exact on these cutoffs. I just care that you don't call more than a standard deviation small. Okay? Those are based largely on the empirical rule and the idea that most of the data lie within 3 standard deviations. Eta. For an independent or a dependent t-test, we have an alternative option. The alternative option is eta squared. And it's the proportion or amount of variance in our outcome explained by our predictor. That's why it's really important, and a host of other reasons, to always be really rooted in what's our research question and what are our constructs that we're studying. If we don't start there, then when we get to our things eta and we're, wait, what is our outcome and our predictor, right? They're hard to interpret. So, for example, if we're looking at the relationship between praise and self-esteem, and we get an eta of 0.25, we report it in decimals, but we interpret it in percents. So if the decimal is 0.25, we could say praise had a large effect on self-esteem. Being in the praise condition, as opposed to control, explained 25% of the variance in self-esteem. Now, why do I love this effect size so much? There's a reason. There's a conceptual reason. Because I'll be honest, most people only teach Cohen's d when it relates to t-tests. But I eta. We'll use it a lot in ANOVA. But there's a really fundamental stats reason why I eta so much. And I'm not going to make you guess it. I'm just saying something. But and it's because it aligns with the fundamental goal of statistics, right? Which is to explain variance in the world, right? So the whole idea behind stats is that people are different. Animals are different, plants are different. People live different stories, lives. We have different experiences. We come from different walks of life. We live different realities. We have different access, right? There's inequity, there's racism, there's poverty. If everybody's lived experience was the same, we wouldn't need to study what we study. If there was no variance, if everybody's income was the same, if everybody's lived experience was the same, i.e. there was no variance, then we would have nothing to research and nothing to model, right? So the whole point is figuring out what explains differences, right? And similarities. And that is what eta captures in an effect size. So yeah, I'm how far part of these group means. That's interesting. But in the big picture question of, I really want to figure out how to improve people's well-being. Well, how much of the differences in well-being was I able to capture? So for me, eta does that in a way that Cohen's d can't do. I'm off my soapbox. So look at this, right? If this is all of the variance in our outcome, then that portion that we were able to capture with our predictor variable, that's our eta. It goes from 0 to 1. In a t-test, what's our predictor? It's just which group you're a part of, right? We only have 2 groups. So it's which 2 groups you're a part of. They're welcome to come in. They always watch tours. Confidence interval, second tool. Any questions about effect size? Not Kramer's V. We'll do that one. Yeah.
Do you think we can just briefly break down the formula of data?
That one?
Yeah.
Break it down.
Like, sort of
You gotta understand what he said.
Can I skip that? Or can I do it on offline? Yeah. You don't need it for now. Confidence intervals. I put these ones on here because they're out of scope, meaning no. Right? I put the questions that you should pay attention to throughout the next following slides. But as I told you, there are no confidence intervals by hand, right? Again, because I care more that you understand how confidence intervals work and the role standard error plays than I do want you calculating pooled variance. And you need pooled variance in order to calculate standard error for an independent t-test, and you need standard error to do confidence intervals, and I don't want you directing all of your cognitive energy to that. So no, no, no. I mean, yes, I can, but no, you don't need to. No, because we're not going to do it. And no, we're not going to do confidence intervals for a chi-square. You can do confidence intervals for something of Kramer's V because it's a continuous measure, but you don't do it for an actual chi-square frequencies because you don't have a standard error. You can do them for effect sizes. We're not going to. Just worry about the confidence intervals. I think I'm going to spring something random that I've never talked about on you. I promise I won't do that. Pretty transparent about what we're covering. So what are confidence intervals and why do they matter? Confidence intervals capture how much certainty or uncertainty we have about our sample statistic or the point estimate, i.e. the precision of our parameter estimate or how much error surrounds that parameter estimate. It's a range of values that to include the population value with some certain degree of confidence. So they look this. In the middle of them is always our parameter estimate or our point estimate. That comes from our sample descriptive statistic. It's the what in our T formula. Yeah, it's the effect, it's the top, right? So it's our mean difference or our difference between the two means if it's an independent test. It's whatever effect we found. That's our best estimate of the population. But then we're going to create a range of values around that middle that are potential alternatives for the actual real population parameter. And that range of alternatives is dependent on the amount of error that we have, right? That's the corresponding. So I think about it a little bit more as it's our lack of confidence or our degree of uncertainty, right? Because the width of that interval is driven by the amount really of error that we have going on, right? You ever heard sports fans, right? This is our bet or think about the election, right? This is the current polling. Here's our margin of error. That's kind of the way to think about it, right? Here's our best estimate of the population and our margin of error. So it's our margin of confidence or lack of confidence. Couple important things. CIs are always two-tailed, right? So if we're talking about a 95% confidence interval, that means we've got 2.5% left on either tail. And a couple vocab reminders, sample statistic. So this is the basic generic component of the lower bound and the upper bound. So there's a line right here, and that line is our point estimate, right? Our population estimate. And then on one side we have our lower bound, and on the other side we have our upper bound. The lower bound and the upper bound are each made up of 3 components. This would be another good thing to remind yourself on your cheat sheet. Those 3 components are the actual sample statistic you calculated, the point estimate, right? Your T, what? Critical or calculated? Critical. Why is it crit? Because that's the thing that's telling you the 95% part, right? So T critical aligned to your chosen level of confidence and standard error, right? That's the part that tells us how much error is around the estimate you've come up with. What does a confidence interval look if this were a confidence interval for a Z test instead? Try it. Just try it. What do you think? Just Z crit instead of T crit. No difference. Yeah, exactly the same. Just be a Z corresponding to 95% instead of a T. Yeah. How do we interpret confidence intervals? I'm going to show you 2 different pieces. One is how we interpret it, confidence intervals, all of them. And one is how we might interpret a single confidence interval, the one you get in your study. So the first one is how we interpret confidence intervals generally. And the reason I'm starting there is because confidence interval interpretation stems from frequentist probability, which is entirely dependent on this idea of doing things over and over again. So it's hard to start by just interpreting one. So the idea is that a 95% confidence interval means that if we were to take 100 different samples, so each one of these lines on the left, right, is a sample. And if we were to take 100 samples and compute a confidence interval for each one of them, so each one of those lines is a confidence interval, 95 of them would have the real population mean, or the real population parameter, whatever we're estimating. So this line right here, that's true. That's the real population parameter. So you can see that of those 100 lines, 95 of them are blue and 5 of them are red. So 95 of them have the actual parameter in them and 5 do not. Now, how many? So if I'm running this one, this is the one I just chose. That's mine. That happens to be my one study, right? Does my one study have it? Yeah. Do I know that? No. So the idea is, what does it mean, right? How confident am I that my one study has it? So essentially, we're 95% confident that my one interval has the true population parameter in it. That's how we interpret it. No chance language. Never chance language in this class. Okay, so we can either say we're 95% confident that this interval contains the true population parameter, or we can say we're 95% confident that the true population parameter falls somewhere in this interval. But it's based on the idea that I think this interval has it, but there's a 5% chance my interval doesn't contain it. Yeah.
So can you say that, not write out, but interpret, make this, if we conduct this study multiple times. So there is, in studies, the interval will be.
I can't hear the true population parameter will what?
In this interval.
No, because each time you conduct the study, you will get a different confidence interval, right? So you can see if you remember, frequentist probability resampling is based on replacement. It's not taking a single sample and doing it over again. It's taking a sample, right? And putting them back, and then taking a new sample and putting it back. So every time you do that, you're going to get a slightly different parameter estimate and a slightly different confidence interval, right? So the dot is the parameter estimate and the line is the confidence interval. So every time you do it, you're going to get slightly different. 95 of those, right? A 95% confidence interval is saying 95% of those intervals will have the real parameter in it, 5% will. Confidence intervals and 0. So someone asked about, hey, can you explain what 0 in the confidence interval would mean both conceptually and practically? One, thank you for that distinction. It's a great distinction because they're different. So let's look at 3 different examples of confidence intervals. Here's the first one. So the first one is a confidence interval from 3.75 to 27.27 with a parameter estimate of 15.51. So here's 15.51 in the middle. It goes from 3.75 to 27.27. Is 0 in this confidence interval? No. So if the way we interpret confidence intervals is we're 95% certain that the true parameter lies in this interval, do we think point blank that 0 is a possible parameter? No. And what does 0 mean? What is the parameter of interest? No, what is the parameter of interest that we're interested in here? Mean difference, right? So it would be no difference, right? So essentially what we're saying is it's not at all that there's no difference here. And that always corresponds with what? P-value, right? I'm gonna use not pink because it's really, it always corresponds with p-value. So if our confidence interval does not include 0, right, then we are going to conclude statistical significance, right? Why do those correspond so closely? Well, because standard error is in the formula for T, right? And 0.05 is our threshold level that corresponds with that 95% level. So they correspond mathematically that way. When we have a confidence interval that does not include 0, it will, or I should say, when we conclude statistical significance, our confidence interval will not include 0. Now let's talk about what happens when we do include zero. Here's our second result. So our mean difference is 1.08, not statistically significant. Confidence interval goes from negative 13.86 to 16.02. Here's our interval, okay? Now, confidence interval includes zero. If we just interpret it as confidence interval includes zero, so it's not significant difference, then it makes it no more helpful than a p-value. Let me say that again. If we interpret confidence intervals as either including zero or not including zero, binarily that, they are no more helpful than p-values. We already have p-values. We don't need them to do that. What we should be doing instead is looking at where zero is in the confidence interval. Where is zero in this confidence interval? It's in it, and where in it? Close to the middle, which makes it what from a probability perspective? Right? So not only is it possible as a potential real thing out there in the real world that there is no difference, it's right because values here are more than values out at the end. That's a key point of confidence. Now, last one. How about this one? Again, if we take the key point of we should be paying attention to where zero is in the confidence interval, not if it's in the confidence interval. What do we make of this one? So good. It's less, right? Still possible. I mean, the interesting thing is it's possible here too, right? If zero weren't in it and it were right here, it's always possible, right? It depends on where we set our threshold. What we know about it being inside is that it means that we're going to get a p-value that's greater than 0.5, right? So the way this becomes very important is because it means it's going to correspond with a non-significant result. So reading the confidence interval correctly almost becomes more important, right? Because it actually in some ways goes against what our p-value is telling us, right? Our p-value is telling us no effect, go home, doesn't work, right? And our confidence interval is telling us, whoa, hold on. Yeah, you got a non-significant result, but the probability of zero is really small. Maybe you should take this all with a little bit of grain of salt. Yeah. So we talked about this. This is a great question, right? Confidence intervals will always have our point estimate, right? Always. They'll always be the middle of our confidence intervals. When values are significant, right? Or I should say when values are not significant, they will always include zero. That always aligns. Yeah.
Well, larger will always relate to like a higher p-value. Just a multi-value way more than they.
Yes, because it will relate to, but why? What's bigger in order to cause that?
Because the probability that.
But what's actually larger that's driving that? Standard error, right? So if you think about a t-stat, again, right? There's a y there. I think it's on the next slide actually, right? Yeah, here, right? The thing that drives a confidence interval being wider is what? More error, right? So either your sample size is small or your spread is big. What drives the t being smaller? More error, right? What drives the test being less significant? More error, right? What drives a big p-value? More error, right? So they're all connected, right? Essentially less of an effect. So the wider your interval, that's a function of more error. Yeah.
So the most useful information out of confidence interval is based on how far zero is?
No, that's the most useful piece of information when interpreting zeros. That whole slide was just about zero in the confidence interval, right? The most useful information out of a confidence interval is how wide or narrow it is, right? Because that is our degree of confidence, right? So what does a narrow confidence interval mean? Yeah, but what does it mean in terms of our confidence in our estimate? Yeah, we're more precise in our estimate, right? A wider interval means narrow. What happens to our confidence interval? Where is that? Someone wrote this question. It was a good one. Where is it? Yeah, here we go. What happens to our confidence interval if sample size goes up? Think, don't roll it X.
Goes down.
Why?
The bubble.
Yeah, perfect. So I'm I'm gonna repeat that because I don't think they can hear you. So she said, as sample size goes up, confidence intervals will get narrower, right? Because confidence intervals inherently are dependent on standard error, right? And as sample size goes up, your error goes down. Now, somebody who doesn't know anything about stats, if confidence intervals represents our level of confidence in our guess, what would happen if you had to just put a stake in the ground? What do you think would happen to our confidence interval as sample size goes up without knowing about standard error? And why? You got it. Why? Why would you be more confident in your guess if you had more people?
Because you've gathered more of the population that you're studying, so you're more assured that you've got an understanding what's going on in the population.
Yeah, don't overthink it, right? That's why I said this was a thinking question, not a memorizing question, right? Yeah, your confidence interval, you get more confident when you capture more of the population. So your confidence interval is going to get narrower, more precise, right? There's a lot of these types of these on this exam, right? They're not meant to memorize. There are a lot of, you've got all the tools and now you're being asked to put them together. We're on our last piece. If you have to go, I know it's really hot in here, right? It's really hot. So you guys are sitting, I'm T-test. We've done a lot of these already actually along the way. So I am going to, I'm going to start with chi-square for time's sake. I'm going to start with chi-square just to prioritize. Because there were a lot of questions about that, and we've looked at some T stuff already and done effect size and things like that. We are not going to worry about effect sizes that are in the book that I haven't taught. So we're not gonna do that. And we're also not gonna worry about, I think there's a follow-up on the DA or the review question that was an error around follow-up testing for chi-square. We're not gonna do that either. So don't worry. Again, it's a general good rule of thumb that if we haven't talked about it and it comes up in somewhere in a book or something, just clarify, but nothing should come as a surprise ever. I have to be pretty explicit about like, here's what I want you to do. So remember, there's just a test of independence, and I told you it's going to be by hand, so you know it's coming, right? Researcher wants to know if participants recruited via LinkedIn exit per survey at higher rates than those recruited via convenient sampling. Below is data from her sample. So source, LinkedIn, convenience, survey status, dropped out, completed. This is a what by what? 2 by 2, right? And we want to figure out how to, this is our, what do we have in our table? Observe what? Observe frequencies. Now, what are expected frequencies in a chi-square test of independence? So these are observed, right? Oopsies. So these are observed. What do our expected frequencies represent though? They're specific. It's not just expected frequencies. It's expected under a very particular condition.
Assuming no relation.
Hold on. But
There's no relation.
good. Everybody get this, right? It's expected frequencies. It's what we would expect if they were not related. Why is that the expected frequencies?
That's the null hypothesis.
Because that's the null hypothesis. Good, right? Everything in stats is against the null. So the null is that there is no relationship between survey status and source. So if we compare everything in stats against the null, then we need to compare our observed against expected under the null, right? And the null is not related. So expected is what we would expect if these two variables were not related. How do we actually calculate expected values? Say that again?
The total of the row plus the total of the column over the entire
Row.
study.
Was it row plus column over frequency times, not. So we have to add them up. So the first thing you're going to do when you're doing this before you ever do frequency should be what? Oopsies, already did my math for you. Yeah, do your marginals, right? So we've got 370, right? We've got 262, 2. This is too much mental math for me. Someone else.
410.
I think it's 162.
See? Can't do mental math. Why? You can make fun of me for this all you want.
370.
Don't tell me, I'm just gonna use a calculator, because otherwise it's just a bunch of numbers being shared. 370, don't worry, all of us on the teaching team, we add up all the exam scores with calculators too, right? 4 times, true, 2 times. What's the total N? 632, perfect, right? And then we add in our frequency of expected, what we expect under the null, right? Row times column over N. And we do that for all 4. I'm not going to do the math out because you don't need to watch me do multiplication, but I did it for you. Here we go. Right? By the way, hint, do you know that if you, never mind. Here are the, I digress. Frequency of observed versus frequency of expected. What do you notice right away before I've been running a chi-square? What do you think? You think they're related, right? With unequal things, just looking at this is really hard to tell, right? Because you're, well, I don't have as many people that dropped out as completed, but here you can kind of tell, right? Why? Because of what the expected represents, right? The expected, the thing on the bottom is what we should get if they weren't related, right? So we can see, well, how close are we to that? How close are we to that? What do we notice? Yeah, I can see just really quickly in my convenience sample, more people completed it than were expected to complete it if they were independent, and less people dropped out. And the opposite pattern happened in my LinkedIn sample, right? So right away, that's telling me I think they're probably related, but I'm going to test it. State your hypothesis. How do I state my hypothesis? You have 2 options. I have TA consensus on this. I don't usually audible this, but I'd like TA consensus on this. Are you guys with frequency observed equals frequency of expected for this, or do you get R independent? I've always done R independent for this, because otherwise you don't know what you're really testing. Null hypothesis for a chi-square test of independence. You don't care. Deja vu. I don't care if you write it this way, but here's the thing, as long as you solemnly swear that you understand what that means. Right? That's my concern with saying, yeah, they write it that way. Right? Because when I was, what does expected represent? The level of confidence around the answer was not what I would want it to be. Right? If I make you write it out, then you have to know what that means. So as long as we know what the observed and the expected represent, then this is cool. So yes, set your criteria, alpha 0.05, 1 tail. Degrees of freedom is the number of rows minus 1 times the number of columns minus 1. And chi-square criteria is 3.84. The reason I told you you don't need a table is because I'm just going to include a screenshot of the chi-square table in the test for you for the test of independence. That's the only test by hand. So rather than make you drag all your tables, I'm just going to screenshot this.
Thank you.
Compute your test statistic. So remember that what we're doing is going cell by cell and calculating the difference between observed and expected. We don't care which one's higher or lower. Note that we don't care which one's higher or lower, i.e. we are not looking at directionality. That comes in later with reporting. We're not explicitly looking at directionality. We're just subtracting one from the other and squaring it to get rid of the negative and putting it over our expected. So how does this difference compare to what we expect? Adding that all together, and we get 10.91. Now, when you do this by hand, you don't have p-values. So the only thing that you can use to compare and draw a conclusion are your chi-crit and your chi-calc. So we can say 10.91 is greater than 3.84, therefore reject the null hypothesis. Source and survey status are related. Yes.
Source and survey status are repeated. You don't want the APA unless you.
So if this is it's not about the steps, it's about the question. If the question is asking you whether source and status are related, you have answered the question. If the question is asking you, please write a APA write-up of this study, you have not answered the question. So rather than thinking about it as do the steps include X, Y, or Z, right? This doesn't have a question attached to it, right? So think about what the question is asking you to provide in the question. If it's asking you for an APA write-up, it will tell you it wants an APA write-up. If it's asking you for if there's a significant difference, it'll say that. It won't say APA. Yeah. This is not included question. So that's, it'd be hard to know. Kramer's V. So if we want to measure, we can also measure max. So this, we now have significance, right? They are significantly related to one another. We also want magnitude. So how related, right? How related is survey status and source. So Kramer's V is the only relationship that we are focusing on for chi-square. It's a measure of strength of relationship between two categoricals. If you know correlation, it's very similar to correlation, but just with categorical variables, right? It ranges from 0, no association, to 1, perfect association, right? And it's a ratio of the chi-square value we obtained, right, to essentially sample size or frequency, right? Sample size. It's unitless. So someone asked what units it's in. It doesn't have a unit, right? Because chi-square doesn't have a unit. It's just a test statistic. And it's just the ratio of chi-square to sample size. So something, a Cohen's D or an eta, it's actually just a standardized unit. It doesn't have a unit itself. So you can't say 0.10 blank, right? You don't interpret the units that way. We don't need to worry about a Kramer's degrees of freedom larger than a 3. That would mean that you have a contingency table that is a 4/6 or a 4/5, right? Because we're using the degrees of freedom for the smaller whatever by whatever, like contingency table. So we'd be working with a very large contingency table, which we're not doing. That would require a really large sample size in order to have enough people in each cell. But you can see, what I care more about is that you can see the pattern and you know why. So why does the Kramer's D get smaller as it goes down? The reason is because your chi-squares just infinitely get bigger as you have more cells, right? Even small amounts of difference add up over time. Chi-squares are summative, right? So those small amounts of difference add up, and that decreasing Kramer's V allows you to accommodate for that, basically. But that's way beyond purview of where we are right now. Write-up. Here's a full write-up for you for chi-square. There are a lot of questions. I noticed a couple of things. Are we going back to slides? Because there are a lot of questions about things that's, how do I write up X, or how do I X, Y, Z? And there are a lot of examples of those in the slides. So just make sure we're going back to lecture slides to pull some of those. This was a good question. On the chi-square slides, I included both a directionality and a non-directionality example. That was just for teaching purposes. There is no directionality in a chi-square explicitly. Now, are you smart humans that make inferences that are not statistically tested? Yeah, all the time, right? If we look at this LinkedIn example, if I told you they're related, convenience sample people are dropping out flies, what would you tell me? We're almost done. Come on, stay with me, right? Convenience sample people are dropping out flies. What would you tell me? You would tell me I'm wrong. Should my answer to you be, but you didn't statistically test that? No, because logic has a place still, right? So the same thing holds here. We're not statistically testing anything. So technically you can't comment on directionality, but you can also be a smart human and infer, use logic, right? So you don't need to include it in your write-up, right? That's not expected in a chi-square write-up. So you'll see my write-up here does not include directionality. So a chi-square test of independence was conducted to examine the relationship between the source of participants, LinkedIn versus convenience sampling, and their survey status, dropped out versus completed. The results of the test indicated that there was a statistically significant association between the source of participants and their survey status. Chi-square 1, 10.91, p less than 0.05. I can only write p less than 0.05 because I don't know the p-value, right? V equals 0.13. These results indicate a small association between the source of participants and their of completing or dropping out of the survey. Cool. I don't even mention direction. Yes. Fine. Yeah. Yeah. Kramer's V. Did I get, is it 0.2? Is that wrong? 631. Which one's wrong? Hold on 1 second. It's right in the write-up. The write-up is correct. Yeah. Yep. Yeah, this isn't the right framers to be. I want to show you a couple more tiny little things that are just reminders. We're not going to go through all of them. You are not by any means required to stay if you're feeling good though. You can go. Please make sure, write these down. Slides 63 through 78. We're not going through them in detail, so look at them on your own, please. This one. A couple of things that I wanted to go through that just have to do with reporting correctly, just some notes. So a department head, undergraduate university wants to test 2 different study mechanisms before the midterm. She gets the Psych 101 professors on board and together they randomly assign half the students to study using mechanism 1, half study groups with a TA, and the other half is assigned to mechanism 2 using flashcards to study alone. Below is the output. First of all, what's the design of the study? Between subjects, right? Between groups or between subjects? Good. Which means we're using a independent t-test. I'm laughing at Jade, not you. Good. Independent t-test. Now, remember that idea of APA doesn't govern writing, it just governs stats. But whenever we are stating a statistical conclusion, we should always report the evidence. So when you get a question, is there a significant difference in test scores based on study techniques? How do you answer that? I'm going to make this expectation really explicit for both exam and DAs. How do you answer this question? So first of all, here's our T, right? Was there a statistically significant difference in test scores based on study techniques? No. What do you report? No. Right? T 18 equals negative or positive, doesn't matter, 0.02. P equals 0.987. Now, stop. Confidence interval notation clarification. Confidence intervals can be made for any parameter, right? Confidence intervals can be built around a mean difference. They can also be built around an estimated effect size. So I want you to notice here where they are. You see that? These confidence intervals belong, These confidence intervals belong to what parameter? What's happening? Difference. To the mean difference, right? So this confidence interval belongs to that parameter, right? Blue and blue. So if we were to draw this confidence interval, negative 0.07 would be in the middle, right? The lower bound would be negative 8.66, and the upper bound would be 8.53, right? We want to make sure that our confidence interval then goes right after our t-stat, before our effect size. If we put the confidence interval after our effect size, it makes us think that it's a confidence interval for effect size. Does that make sense? Very small. I'm not going to penalize people for that. It's just a good FYI. The other thing you can do if you want is 95% CI. Sometimes I will even write it in the either just 95% CI or 95% mean difference CI if you want to actually write it out to make it really, really clear what it is versus, so you could, if it were a mean difference CI, right? So there's 95% mean difference CI, or if you were doing an effect size CI, 95% effect size CI, that negative 8.66, 8.53, D equals 0.01. That is the complete answer. All the stats, right? Now, yes.
Is the mean difference in there technically 0.07? Is it a positive?
It doesn't matter.
So it's not technically negative?
It doesn't matter. Yeah,
It's theoretical.
it's not theoretical. It's just which ones.
With the confidence, oh, because it's not what's in the middle of it.
It is what's in the middle of the confidence. Yeah.
So it doesn't matter if it's negative.
Are you talking about for the confidence interval or for the mean difference?
Yeah, I'm visualizing that number in the middle of the confidence interval.
Yeah, so the mean difference as stated goes together with the confidence interval as stated. If you're gonna change the mean difference to be positive, you will have to tweak the confidence interval.
So I think you have following the effect size. We have the following.
So my short answer is yes. My longer answer or my more comprehensive answer is, and you'll hear this from me a million times as we get into write-ups, is I never really care how you report things as long as it is clear to the reader, right? So for example, if you moved, where did it go? If you moved that confidence interval to the end, but you wrote mean difference confidence interval, I don't care, right? It's just making sure it's clear to the person who's reading what the confidence interval belongs to. That's the guiding rule of thumb. Yeah, cool. But this is a common trap on the exam all the time. People are, no, P less than 0.05. That's not stats, right? You need the whole thing. Whole thing. Another trap is, when I say traps, these are good things to write on cheat sheets as reminders, right? I need T, degrees of freedom, my T value, my P value, my confidence interval, and my effect size. All of the stats always, right? Not just for exam, but for life. Making sure you always include your outcome variable names and your predictor variable names. So if you're interpreting a Cohen's D or an ADA, you're not saying 10% of the variance is explained by this. 10% of the variance in what is explained by this, right? Our brain heuristically fills in gaps. That's a common thing we do. It's not bad, it just happens. But making sure that those gaps don't end up on the page is important. And that's an important thing, not for an exam, just for when we write manuscripts. That happens to me all the time. I write things that I think are missing or are there, but they're missing for the reader. I think that's probably it. Only other thing that I saw in DA4, y'all, is being really careful. Wow, time for me to go. Is being really careful about what your null and alternative hypotheses are for independent t-tests and dependent t-tests, right? So a reminder that for a dependent t-test, it's one parameter, mean difference, right? It's that the mean difference is equal to 0. That's our null. For an independent, it's that the mean parameters are the same. They're equal to each other. All of that is in here. So I put it all in those slides I told us to review carefully. And then I think that's it. Yeah, so Daisy, to your question, you'll get something this. If it's write it up in APA, it'll say write it up in APA. And you'll see, by the way, here, this is a checklist. You can add it to your cheat sheet. Guess where I got that checklist? Not my head. Model building guide that I already wrote for you that's on the website. Guess where I get the examples of how to write up stats? Model building guide. You have it. It's a good resource. Good if you're struggling with how to write the stats correctly, all the examples of how to write that are in that guide, including annotated write-ups of how to write it. Yeah.
For a dependent hypothesis write-up, can we do time 1 and time 2 equal?
No, well, for dependent, no, because that's not your parameter of interest, right? You're not interested in estimating two different means. You're interested in estimating, because your hypothesis is not about your sample. Your hypothesis is about the population.
Okay.
And what you're estimating is average change in a population. Yeah, cool. I'll stick around for a little bit. Don't forget to review those slides we didn't hit. Yeah.
Just ask 2 questions on that. Example 1, interpreting Cohen's D, and then the one.
Which one? Oh, yeah. This one? Oh, yeah. This was a good, I'm gonna keep going for people who want me to keep going, but TAs will be here too. If people have other questions. If someone jumping online, you would interpret it the same. What's your instinct? Yeah, you can be, it's a negligible portion of a standard deviation.
And then. My study, I can't say so I have studies.
Yeah, I mean, it would be like if you actually, what would it be if you actually calculated it? You would still calculate it and report it. So it wouldn't be an automatic 0, right? You would still be, so.
Yeah.
Oh, it's squared, it's just square.
I know what the formula is, but thank you.
It's calculated.
That's what I'm doing.
You actually get it, whatever. For significant zero. And then essentially, but I think just even doing the things, it's almost zero. It's zero, 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 so you would just say something like, not for. That is something I write like some narratively. Try to be something like that. I don't know about this stuff. Yeah, are you on campus or leaving right now? I'm supposed to be with Priscilla. Yeah. Using your. There's a different side that you can do for changes. So that Adidas, that a variant vector. It's going to give you that. If you want to calculate it, you would just do.
Oh my gosh.
Talk about back size and variance in terms of like how you want. Yeah, but not yet. But we will do. And you're not see it's picture.
Describe power as a. On the concept.
Still, it's still this, the different ways, but it's still not. So if you get over there.
All of us, so there's here an APA, which is that section is really fair for the exam. You guys are gonna go in and certain manuscripts and these. So it's very important that you do report certain things in a certain way. Yeah. In a certain order. So you might have got a deduction on the PA, but don't worry so much about that on the exam. Please focus more on the conceptual background.
Wait, I do care about it.
Oh, okay, excuse me.
Yeah.
Right, yeah.
You're doing that right now?
Yeah.
Yes.
Wow. Is that what we should do?
It's just. I guess it's somewhere more.
A lot.
Yeah.
Backside or outside? Yes. Yeah.
We don't have this.
Can I see your feedback?
Oh, that's true.
Me. Yeah. Yeah.
It's still.
Small.
I know. Right. It's fine with the public everywhere else. Yeah. Yeah. Same here. So, but specifically, about or the scanning. So, I go, right down to my big, we ran it.
Wait, circle 16 and what?
16.
Oh,
And see.
yeah.
It's not a post. So. Where. Yeah, and have a name where we recorded, put it, but the standard deviation of. Yeah, that's right. I don't have next. That's how. I wonder, I did in the.